Thank you, Dieter, for the insightful presentation. Next, we will have a panel discussion on an exciting topic, the ingredients of deploying learning-based robotic systems in the real world. Despite the substantial progress in the field of robot learning, the large-scale deployment of learning-based robotic systems remains limited in the real world. Our panel today will explore the essential components for building reliable learning-based robotic systems. Our discussion will touch upon several important issues, including what are the key challenges in deploying learning-based robotic systems in the real world? How can we ensure the reliability and robustness of robot deployment? And what can we learn from the success stories in the deployment of classical robotic systems? It's a pleasure to have a panel of experts here with us today, including Dieter, Emil, Nicholas, Russ, and Scott. It will be moderated by Jianlan. Let's welcome them on stage with a round of applause.
Great. Let me on behalf of all the audience and organizers, thank you again for your time, for being here. Take the time and your diverse view aspect of this really make us learn a lot. So we'll go today. I will first ask you one question to each individual of you, and then we'll go into more sort of like a free format. So my first question actually goes to Dieter. Dieter, you have been in this field for over 30 years, and you have done seminar work in many areas of robotics.
More recently, counting numbers right now.
So
yeah, kind of.
More recently, you have focused more on the topic of simulation as you presented in the talk. Isaac Jim Factory, a robot can now learn solely from simulation, very impressive textual manipulation skills that are previously known very difficult to simulate. How do you see the role of simulation in deploying robot learning system? To which extent should we rely on simulation data, and what's its limit?
Yeah, well, for those who heard my talk, you saw some of that, and I hope I kind of fairly acknowledge also clearly the limitations of simulation. I mean, one of the reasons why we're doing a lot of work on simulation is just also for practical reasons, right? It's really hard to train robots, as we know, in the real world. It's expensive, it's time consuming. Simulation has, especially for learning, of course, various advantages beyond, let's say, the benchmarking here, right? Like if you, especially nowadays, what we see more and more is, for example, that imitation learning is kind of seems to be the go-to technique to get robots to do like a really broad range of things. And this is both with what we see, for example, out of the RTX models coming out and things like that. Again, imitation learning is very powerful. So the question is, for imitation learning, if we ever want to scale that to the level of what we see in the language models and vision models, we need huge amounts of data. And there's efforts going on collecting all the data, of course, in the real world. As an example, and I think it's great, and we need these large data sets, but at the same time, it's still tiny compared to what many of these language and vision models are. And at the same time, randomly generate environments, you can generate tasks, you can generate, for example, reward functions to train your system. You can use something in another talk about like task and motion planning to solve tasks in simulation that we example, hopefully to train these large-scale models through imitation learning. So that's, I think, one of the ideas is really just the ease at which you can scale things. And especially now looking at again, the developments with generative AI, that it's actually a huge plus also on the simulation side, because with generative AI, we can make the assets look much more realistic. The environments are going to look more realistic. We can automatically generate these tasks, right? And I'm sure some of you have, for example, seen Eureka is one of the examples where you can use large language models to even generate code for reward function generation and things like that. So um, I think scaling is just a big, big plus from my perspective. And scaling, as we know, is important for learning.
Yeah, but I think you touched multiple important points. I certainly agree that the easy of generating data between real and sim is actually particularly huge. But also there's a point like of the data quality and the realistics and those type of stuff. We'll go to the point when we into the free debate, free panel section. Uh, my next question actually goes to Scott. Uh, Scott, the Atlas result you showed this morning were truly impressive. Now I wanted to touch on a point that is of particular concern when deploying such robotic systems, robustness and stability guarantee. As someone doing controls, so one question we must ask ourselves deploy any system is what type of a robustness guarantee the system has. And we have developed a set of tools and principles to deal with that. This Nyapanov stability, and there's a whole subject of robust control. Uh, However, when we actually build these systems, we found that some of these assumptions were just way too strong and didn't align with the real world well. So we then kind of dropped these theoretical guarantees and then resorted to empirical engineering solutions. So, but on the other side, one of the biggest concerns of deployed learning-based system seemed to be the lack of interpretability and robustness guarantees. How do you view these contradicting points? And what can learning-based system borrow from the success of deployed robotic system with classical approaches?
Okay, cool. Nice question. So I guess I like to think about robustness and stability in a kind of statistical sense. Like I'm pretty sure I'm not Lyapunov stable. I don't fall very often, but sometimes I do. Yeah, and I think if you have the ability to do things like large scale simulation validation of systems that already exist, test lots and lots of parametrically defined cases that you think the robot might experience to identify corner cases, and then track how the system performance changes over time as you make changes to it, whether that's through a learning process or through, traditional engineering changes. I think this is all very important. As I mentioned in the talk, we also supplement, simulation-based testing with pretty extensive hardware in the loop testing. And so we take it upon ourselves to have a large fleet of robots that are doing a variety of tasks that are things that statistically come up very often in most deployment scenarios, and we are able to have efficient reporting systems that collect data from those runs and report them back, and so that we understand very well how changes are likely to impact customers before we ship them back to them. But nevertheless, robots do fail, right? You put them in a customer site, it is not the same as your robustness lanes, and things are going to happen. And so having the ability to, as much as possible, allow for graceful recovery in the field so that customers can get the robot back into a working state again as quickly as possible is really important. And then having good systems for reporting back, salient signals and logs so that we can analyze them and root cause them and then ship solutions back is also extremely important.
Robustness is truly a very important question, and I guess you touch a point that I cannot agree more. Well, it's unavoidable that theory and practice always have some gap, but by the end of the day, we all live in Earth. So if we break something really hard, 1,000 ways, 10,000 ways, it does not break. And if we run something for 10 years, it does not break, maybe that's a good thing. And we're sure we'll come to this topic again in a free panel discussion. Next, I want to ask Ross. Ross, I wanted to ask you about perception and learning. For control system, we know there's something called separation principle, which separates the problem of state estimation and control. Well, it doesn't generally hold true in nonlinear case, but we use it anyway, because that's how most of our robotic systems get deployed today. Because it's just so tempting to build a better and better state estimator and pass it to you through a low-level control system or whatever. However, the perception and the control loop are loosely coupled there. However, since around 10 years ago, the advent of deep learning made us to process perceptual data differently and very differently. And presumably now we can have a much tighter perception action loop, which arguably will result in a much more reactive and robust system. How do you see the role of learned perception in deploying robotic system today? Or more broadly, on which component of robotic system should we actually trigger the power of learning?
Okay, let's unpack that. So let's take learning out for a second. I think we know how to formulate output feedback problems. If you give me a model, you give me a model of my dynamics, you give me a model of a sensing. We have known for a long time. I used to complain to Scott years ago that the reason that even legged robots are fragile is because we're still building better state estimators, and we need to break the. I was always saying output feedback, and then finally I switched to manipulation because there everybody understands output feedback. But in because you can't build a state estimator for making a salad, right? But so in my view, let's say maybe just to say something a little bit controversial or something, I think perception really is just a subset of control. And if you solve the control problem correctly, which is the mapping from output, histories of observations to actions, then you've solved the representation question and the perception question. Now, we don't do that well enough, and control theory hit hardness results and proved it was really hard to do that. So we didn't do enough work in that direction. I think where learning has absolutely changed things. First of all, RGB is a terrible space, and you shouldn't try to work with it with like derivatives and other things. So getting from RGB back to some other representation, absolutely learning changed that, right? And I also think that just the emphasis on learned representations and breaking away from representations that were encoded in physics directly and going to these latent vectors. I mean, that was always, output feedback should have always solved that problem, but we found lots and lots of new. We've just sort of thrown ourselves into the domains where you can't use physics-based representations, and we've seen it's okay. You can actually learn representations, close feedback loops at high rates through them, and it's awesome, and it changed things.
Sure. When I first touched control, studied subject for control, like without perception, I think control is more or less like this is also controversial solve. Like but not solve, but basically anything you solve, you think about something, you will find something in the literature, in the reference, someone has solved it deeply. But with perception, things have become differently because most control theories they don't deal with perception and don't deal with images. I also agree with you that RGB space is actually a quite large space for you actually doing control. For you to do control, you really need probably a very tiny fraction of the RGB data, and then you need to learn a suitable representation. And that's actually a very timely important topic we will revisit in this panel. Okay, next I want to go to Nicholas.
What's that?
You said put learning aside for now.
Oh, I sorry, I tried to do it at the end. Yeah.
Oh, okay.
Sorry.
I
Learning
still
came
was-
back when you get out of RGB, right? So I think RGB. I don't have any control techniques based on sums of squares, let's say, that works with RGB images. Okay, not directly. You can get from RGB into something that sums of squares could work with. And then I think the emphasis on learned representations. I mean, okay, let's see. Learning brought bravado into the field in a way that was like really good, right? It changed everybody's expectations. People were, trying harder problems than we ever tried before and got us out of a local minima, and that was just fantastically good. But in terms of like what we know today, do you need learning or not? I think in the question specifically about perception and state estimation, I think it's getting out of RGB and using larger data, pre-trained, contrastive visual, you name it, to find representations that would have been hard to discover purely by solving more narrow output feedback problems.
Next, I want to move on to Nicholas, and I want to also switch the topic a little bit. So, Nicholas, I wanted to ask you about foundation models, which I think many of us are very interested in this topic. So, with models like RT1, RT2, RTX, we know robotic foundation models can utilize large-scale, multimodal, multitask coarse embodiment dataset, which is unseen before, and push the generalization capability to a greater new level. Despite that, these models have not shown that 99.9% reliability yet, which is crucial to put them into practical terms. However, your recent work, Robotic, is a foundational agent that can keep improving itself to reach higher performance if desirable. So can you comment a little bit on the opportunities and challenges to deploy these models into real world?
Right. Yeah, thanks. I think there are actually a number of challenges probably at this point. We're only just beginning to understand how to work with these models, what they can do, and so on. I think ultimately, so at the moment, generating data is certainly one of the main challenges, and that's something I think that many people are thinking about. What kind of data sources can we leverage? I feel we need to get to a point where we use small amounts of the expensive robotics data and large amounts of other more cheaply available data, not just for the semantic reasoning, but ideally also for the control aspect itself, right? So different foundation models may be focused at the moment on different aspects, either at the motor control or the semantic understanding. I think the semantic understanding will probably have more easily under control with the data that's freely available on the web, and the motor control is the challenging part. So coming up in particular with strategies to leverage alternative data sources here, and maybe simulation could play a role there, and actually sidestep the sort of slightly awkward sim to real paradigm that many of us, including myself, are engaging at the moment. I think where we would like to get to, I suppose, is that ultimately these models can be optimized for a new task with very small amounts of new data, right? That's really where we would like to get to. Whether self-improvement and maybe even autonomous data generation will get the models to a very different sort of performance level, like the 99%, I can't tell you at the moment. So I think that's something we have to see. I think at the moment, probably the data that goes into these models doesn't even have the required performance that you're asking for. If it had, I don't see a reason per se why we couldn't at least fine-tune a model to achieve like very high performance on a narrow task, right? Maybe even eventually with small amounts of data. Yeah, I think then there are other challenges that have maybe not to do with data or the performance of the model, which have more to do with inference and maybe also the control rate that we can achieve with the models. So at the moment they're difficult to deploy. They certainly couldn't be run, or most of these models couldn't be run at the moment on a mobile robot that has no internet connection. And they also, even when you have like a large compute server available, you can't run them necessarily at the right frequency that you would need to solve more agile or more dexterous tasks, right? So I think there are lots of opportunities, but also still a significant number of challenges at the moment.
You comment a lot on the data side, where I think most of us agree that grounding with web data, grounding with utilizing other sources of data. But do you see any challenging that in the algorithmic side? What type of algorithmic development? I mean, of course, we have a debate this afternoon. Is scaling all we need? But do you see more come from that side as well?
Yeah, I mean, like a few obvious things that come to mind. I think relatively little work has been done on truly multimodal models, and maybe some architectural innovations might be needed here. I'm also not sure sort of the aspect of control rate and how we structure decision making over different temporal scales. Again, that's something that hasn't really come up very much, right? So we don't have dexterous models that can also do reasoning, basically, right? So that's mostly been treated in isolation with existing models, at least from what I'm aware of. Another one is sort of the data quality. So what I meant to say, that this might again need some thinking about model architecture, for instance. Another aspect is I think the kind of data that we're training from. I guess at the moment they're trained with BC, so they require expert data. And again, that doesn't necessarily feel scalable. It also makes the data harder to transfer across tasks, right? So I think maybe scaling is what we need, but we also need some smaller or bigger innovation about how we use the data, basically.
Yeah, I think that makes a lot of sense. So now I want to ask Emo. Emo, most of us get to know you by your work on musical optimal control, and I myself learned the algorithm iterative LQG by your paper. You have been advocating triagionization, which is a powerful tool to solve many robotics problems. There you also agree that some of learning is needed, be it call it the term system ID or in other formats, because there's always certain degree your model can be sufficiently accurate. My question to you is that how would you think we should combine model-based approaches with learning-based techniques to take the best of both worlds?
I mean, so first of all, what people call learning today is optimization. So not sure the difference is there. Question is what you're optimizing. One other brief comment before we get into that, adding to what you asked Dieter, why do we need simulators in the first place? If you come from a world of model-free learning, that question makes sense. If you come from more traditional control theory, that question does not make sense at all, because to do model-based control, you need a model by definition. Like you need quantities like derivatives and various other analytical things that your robot won't tell you because there is no such sensor that measures them. So there are lots of types of control that you can only do in a model. So like that's that. But focusing on model-free learning, yes, I think it's a legitimate question. You know, how much do you use one or the other? Now, optimization versus learning. So again, the same algorithms that you use for one, they're also used for the other. Whether, I mean, perhaps you think of optimal control as, let's say, optimizing a sequence of states or a sequence of linear feedback gains, versus learning where you optimize the weights of some neural network. If you actually look at what you do, you're doing the same thing. It's just a function with a bunch of parameters. You're applying the same algorithm to it. So pick whatever representation works for you, and you know, good luck to you, basically. there is no reason, like in other words, you don't know in advance what's. I mean, you should obviously use the simplest thing that works for a given problem.
I know you have an algorithm take to tail, which is a simple thing, which is basically trying to dump this thing that is not entirely stupid and to see if that works. If it works, that's a simple thing.
So yeah, speaking of not entirely stupid, so I really like this new thing from DeepMind that Yuval Tass and company did. It's a variation on older things like MPPI. So basically, you do trajectory optimization by trying n trajectories, picking the best, and then try some more. So that's about as dumb as it gets, and it's actually shocking how well it works. And I think that should become a benchmark for stupidity, right? You know, if your if your learning algorithm is worse than that, then you really need to quit that algorithm and try something better.
But what if I just want my thing to work? I put a model and then I try to differentiate it through a contact in the real world. I just found out I cannot find the gradient. It's not differentiable. And should I do learning or not?
Wait for the next release of Mujoko when it's differentiable.
That's a very good answer. Okay, so we'll enter the free discussion. So we don't have I just have a very loose topic. Every speaker is free to take the microphone and speak whenever you feel the moment. So I guess the general thing I want to really talk about is that out of which we have all talked about simulation, robustness guarantee, foundation models, data, control, perception. What are the major blockers preventing us to adopt learning-based robotic systems into the real world?
I'll say something quickly, which is basically what Dieter said in his talk. We see all these wonderful videos. They kind of look good. Is this real? Is it a lot of hacking? Is it overfitting to a lab? Like, there's a difference between the demos and what happens, and the person who makes things happen in the real world wants to say something.
No, I basically agree with that. And from our perspective, it just has to be better. The output, the behavior has to be better than what we can generate otherwise, or it has to be at least similar and easier to generate, right? So we like to think about this both from like an engineering effort point of view. as well as the ultimate performance of the system. And there has to be some reasonable trade-off for us in order to pursue one technique over another. And for a long time, there was a sort of obvious answer that was purely model-based control. And I think things are starting to get better where we're now starting to use RL, as you can see, to deliver some capabilities in our robots. And so I think just having the flexibility to apply the right tool to the right problem is the important thing. I don't really, there's a lot of talk about interpretability and how like a learned policy is somehow a harder thing to field. I'm not totally sure about that. If you look at like a really capable, like deployed control system that does a lot of complex tasks, it's also a pretty complex thing to analyze. You know, there may be modules that have signals within it that you can interpret and target, you know, do fast engineered descent. But it's also pretty nice to be able to have a policy and be able to understand failure cases in the context of how you might augment the training distribution in order to improve performance. And then as long as you have exhaustive testing on the other end, you can be pretty confident in the changes that you made. So I don't know, I think we're pretty optimistic about, at least in the near term, a sort of mixed picture of both learning and non-learning based techniques delivering cool robot capabilities.
I actually have a question for the controls people here, because Emo said that it's all the same, right? You're optimizing for something, and that's of course right. But then at the end, also the architecture of your learning algorithms and all that really matters, right? And what I like about models, recent models like large scale transformers and also diffusion kind of models is, and why we're using it for almost everything we do these days, is just also the flexibility, right? Where you can feed in multimodal data, you can combine language with vision, with prompting, you can connect it to large language models that are pre-trained already. And at the same time, it feels like if you can generate enough data, they're going to be able to do something with it, right? It's really hard to find kind of the limit of what they're able to do. And my question is, so we see this, that they start generating maybe some kind of policy output, but from a controls perspective, how far does it make sense to go with these kind of models, right? Is it conceivable that, well, even the lowest level 100,000 hertz controller for my manipulator should be some transformer? Does it even make sense? And are there maybe capabilities that these transformers might bring to a lowest level controller that are also beneficial? And that's really a question. I don't have an answer.
I can start. So, I mean, obviously, these things are great and we should exploit them. I don't see them producing motions of the quality that you need to control a robot. I mean, they don't even produce language of the quality that you want. It's basically a giant BS generator at this point, which is really polished and sounds really good, but the content isn't there. But the way I see it is that they're going to give us useful hints, which can be used as a high-level control to things to guide the NPC, for example, that Scott was running, or to guide some other like trajectory optimizers or whatever. Basically, I think we need the control approach to actually drive the real thing in real time, and all the learning is basically a hint to improve it. If you want just the learning to go all the way, I would say we don't have the data. I mean, that's the problem. We don't have the data, right? And we don't have the way to generate the data. In fact, one place where we kind of seem to have the data, if you look at the Tesla self-driving thing, that's kind of the exception that proves the rule, and the rule is that it doesn't work. So Tesla kind of works, but what does it do? What do? They have 500,000 humans teleoperating their robot. And instead of paying their human subjects to do the work, the actual human subjects pay them. That's the brilliance of Tesla. And so the simplest possible robot is, especially since they're keeping it out of the crazy dynamic regime, they have to develop their own supercomputer to do it and all that. And so you can see what it takes to do real-time, and still they're not completely doing real-time control from learning. Like they have models and low-level stuff, but I think that's kind of the quality of data that you need to really have a learning approach to work in robotics. And it's just not realistic to get that kind of data outside of massive teleoperation.
Okay, I'll answer completely differently just to keep it interesting. Okay, so first of all, I think the thing that changed, I mean, we know this, but in my mind, the thing that changed when we get to the really large models is that the optimization landscape seems to have fundamentally changed, that we're able to solve problems that we would have said were non-convex and unsolvable before, and we're winding our way down high-dimensional landscapes. And I think the theory of ML people are doing a great job. There's a lot more to do in understanding what the heck just happened, right? I think there's some really important things that happen at the control when you do that for control, which I think we were also a bit short-sighted. And maybe if I were to pick one, I think, well, solving one task could be harder than solving all the tasks. Okay, so we used to say this in trajectory optimization too, like stochastic trajectory optimization is actually potentially easier than deterministic trajectory optimization, because if you're deterministic, then you can have all these little corner cases and local minima. But if you have to like have an ensemble of trajectories all get the same solution, the optimization landscape comes out. And now if you have to have the same policy that can roll the dough and spread the sauce and do all the things, that might actually be easier, and you might actually be more robust when you're done than if you just spent all the time trying to spread the sauce, or just pick one of those tasks. Okay, so I don't see any fundamental reason why that shouldn't be true at a lower level too. I mean, and a lot of times the optimization landscape is relevant for training, but then you can compress the heck out of these things later and get something. If it's just about runtime rates, I'd be optimistic that those things are being quantized and everything like that, right? So we have a really good, like if you're just trying to send torque commands to the motors and you want to, you know, work around a sloppy transmission or something like that, we have a really good solution right now. So it'll take a while till we want to replace that with something different, but I don't see any fundamental reasons why those insights shouldn't go all the way down.
Yeah, I mean, I agree with what was just said. Maybe the small thing I would, or two things I would add, I guess, what's really good with these models is sort of the optimization landscape when you have the right target data, right? What we don't really have at where the target data comes from is still another question. That's maybe will be made easier by these models as well, if they can help, for instance, through some self-improvement loop or not. I guess at what level they make sense to apply, I suppose ultimately it depends probably on the generality and the diversity of things that need to be done, right? Whether you need a model that can absorb large amounts of data to sort of reflect the functionality, and if that's not necessary, maybe then also you can get away with something smaller or cheaper.
Just one quick comment regarding also this target data. That's also related. I think Russ made a really good point regarding the kind of supervision we need. I think even if we could generate, let's say in simulation or whatever, like huge amounts of data, I think it's still actually an open question. What level of supervision should we give to these networks, for instance, right? Should we give them, let's say in simulation, you can give the perfect supervision of ground truth states and everything is known. And the question is that actually going to be better than just giving them high level, let's say language style supervision, right? It's not clear to me. As Russ said, counterintuitive that it seems easier to learn from many tasks rather than one task. It could be, it's easier to learn powerful models from weak supervision than from very strong supervision, right? It's just, I think it's not clear.
I have to object to this trend that's developing here. So you guys, you guys are saying that if you gloss over the problem and make it fuzzy and nice, it's going to kind of become a nice ball and your optimization will go there, which is true. But the solution you get is not going to be as good as the solution that you would have gotten if you focus on one problem and developed a really powerful optimizer that handles those corner cases and that landscape. Why do really?
Yeah, I disagree.
Wait, so you're telling me that you're going to train one policy on 50 tasks and you're going to give me that one policy and I'll not be able to find an improvement on one particular task?
I will make, yes, I'm going to say yes. I'm going to say yes.
Okay, give me that.
See, you tried to hand the mic that way. Right. So first of all, okay, so you sort of stuck in there like a sufficiently powerful optimizer, but I think the optimization landscape is worse if you focus on one task.
Yeah.
Okay. And I think, okay, then you could just say that, you know, I will have seen more things if I trained on n tasks. Even if you take this, if you normalize for the amount of data, right, there are going to be more things that your robot might have learned to recover from, for instance, right, than a narrow specification on one task. And I think, the thing that GPT showed us all, maybe some of us saw it earlier, some of us had to get thumped over the head by GPT to see it, but is this like common sense capability that is just a different level of robustness than we have in a control system that was designed to narrowly play ping pong or something like that. What happens when the ping pong ball falls or the paddle breaks or something like this, right? That you didn't have your single skill that handled the case when your ping pong paddle broke and you had to, like, I don't know, go get another one or play with your wallet. But I don't know what you're going to do. But there's just like out of domain, out of distribution stuff that I think you could capture if you train multi-skill that you won't capture if you train single skill. And that will fundamentally make you better at doing every single skill.
Do you want to, actually, because you also, I agree with Russ, and it's just, it's overfitting, right? Like if you train a system on a narrow domain, then you're not gonna get good generalization.
For overfitting.
No.
You want to do it fast.
But we're talking about the learning algorithms, right? So what we see is if you give them a very super narrow domain of data, then they're gonna just overfit to that data and they're not going to generalize well. And we see that in the language domain that I find this kind of, let's say, word prediction is actually very weak supervision, right? And I think we all agree that what comes out of this really easy training model is pretty fascinating. I'm not saying it's perfect or anything like that, but it is pretty amazing. And I guess there's this notion, if you throw enough tasks at the system and you don't constrain it by saying it too explicitly what nitty-gritty details it should reason about, then somehow there's also some kind of internal representation emerging that just captures the essence of these tasks rather than what you as an engineer thought are the things it should learn. But we'll have to see where this is going then.
I agree in principle, but I would add a small caveat, which is that, so what I think we haven't really understood very well is, for instance, how sort of the what you call the weaker supervision, the language, the semantic level, and maybe the common sense reasoning interact with the motor control, right? So if you're ultimately interested in producing movements, whether the robot will easily generalize or whether the robot will generalize to new movements just because it has some understanding, some high-level understanding of the world. I think that's the bit that we haven't studied very well, right? I'm sure it will be able to sort of, the model will have the knowledge maybe to handle the out of distribution situation when the paddle breaks during playing ping pong, but whether it then is able to, I don't know, move its arm to play with the bottom end of the ping pong paddle instead is a very different question, right? And I think those types of generalizations and transfer is I think something we'll hopefully be able to demonstrate eventually, but it's something we haven't seen very much, I would say.
Let me ask a question to Scott, actually. So you mentioned this magic selection box that was engineered by very smart humans at Boston Dynamics. How would you compare that to just trying to learn that things from scratch and not engineering it?
You could definitely just learn it if you wanted to, right? So this is basically human in the loop learning, right? They're taking empirical data, processing it through their brains and experience and intuition and coding things over time and then running tests to validate it and iterating. So you could remove humans from the loop, and essentially that's what we've done. Yep. Just to go back to that last discussion, I wonder if there's, at least in the medium term, always going to be this trade-off between generalizability and performance in a particular skill. And this is maybe what Emma was getting at, where, you can take an average human and, put them in front of a soccer ball and say, kick it into the goal, and they'll do a decently good job at doing that. But they're pretty far from a professional soccer player. And so I think maybe it's certainly, I think, the case that we want to build models that allow the robot to generalize and have a good shot of doing zero shot, few shot, manipulation, for example. But I think also supporting avenues for refining behaviors to very high performance is also going to be pretty valuable for the kind of robots that we want to field.
I completely agree. But I think robots are going to be super useful by being the average human. And I would love to see us get there first. And then I think we're going to have our specialists that come. You must, like, you must be able to do better if you narrow the distribution of domain and you get to fine tune. And that's, we have human specialists all over the place. So, but I would say that because the potential robustness that comes from being a generalist is so powerful and so different than what we've seen before, I think we must do that first. Because if you specialize too soon, then you could miss out on the bigger prize.
I have a question actually on this, and whether we have a good idea. Maybe this relates to the question that you asked earlier. Do we know that it's got to do with the models that we don't achieve that high performance, or is it maybe the data that we are sticking in? Are it perhaps really stupid reasons that, I don't know, the perceptual encoder doesn't give us the necessary resolution? So I'm just wondering whether it's really something about general versus narrow, or more about maybe other things that we're getting wrong at the moment.
One answer I would suggest that we're stuck with stochastic gradient descent for some reason. That might not be the best way to do things. Just saying.
So what limitations do you mean exactly? I mean, the behavior cloning stuff we've seen is just phenomenally good. I mean, there's not a task we can put in front of it that if you give it your 50 to 100 demonstrations, that it's gonna do a pretty darn good job in the domain of the training data. But well, I don't see the limit maybe that you're seeing or you're saying.
Well, to clarify, actually, maybe what I was trying to say, I don't see that limit either, but it seemed to be implied by the discussion just now that we're sort of the performance is missing at the moment, that this has something fundamentally to do with the modeling approaches that we're taking. And I'm not sure about this, right? That was actually my point. Maybe we're trying to expand more broadly, but maybe if we just had the right data to optimize the models with, we would get appropriate performance.
I agree with the notion that the data seems to be the key limit right now, right? So like you can train these policies and they can do very well on these individual tasks, but I think where we need to go, and I guess most of us agree, is just broader sets of data, right? So that we can train these models.
But so what you guys are saying that if you already have an answer, you can train a model that's going to give me the answer back, which I already gave you in the form of data, which is very kind of you. But I would like to solve some things that are not in the data, right? I mean, that's the whole point. Like, you have data on the internet in language. You don't have data on a robot with specific actuators and whatever doing the task. Like, that's never been done. You have to discover it. So you can't just, like, behavioral cloning, sure, you can overfit everything. Well, let's not call it overfitting. You can fit it to arbitrary precision with enough parameters. But one, the data has to be generated, means that that robot has to do the task independent of your learning. And two, how you're going to interpolate or extrapolate to other things if you overfit some very specific high quality data.
I'm a little less worried about the data quality than Dieter. I think we don't know the answer yet, but yeah, okay. Amount, I think we also don't know what the scaling laws are going to be, but I'm even optimistic about that too, just to further offend Emo. I mean, I think right now we're taking 50 to 100 demonstrations to learn a new skill, but then as you've learned, 30 skills, then maybe that number goes down, and adding the 1,000th skill should be a few demonstrations, but certainly way less than 50. So I guess, I'm optimistic about that, right? And it's doing more than giving us back what we put in. So the human is putting in something very valuable with their demonstrations, and I think we have to do more than that in the long run. But I think the question is, how far do we get, even if we do that? Yeah, and I to the specialists versus generalists, I actually agree with you. I don't know. I mean, I wasn't trying to make a capacity argument. I think we can make the models arbitrarily fine, so they could be extremely good at recovering the behaviors and all the narrow things. But I still think at some point there is some limit where you can do better by fitting to your narrow distribution than you can do, not because of capacity, just because the decisions you will make will be fundamentally different. If you know that, I don't know, we did some work with Amazon and talked about their different data sets during peak versus whatever. If you know it's peak and you know there's going to be more whatever in the boxes, then you can act differently than the generalist would, because you have extra information available. It's not just a capacity argument.
Should we take some questions from the audience?
Yeah.
Yeah, we can. Anyone want the audience have some questions?
Should I?
Okay. Yeah. Hi, and I'm Geyan, and I'm a second-year master student at UC San Diego. And I have a question for Professor Derek Fox. That I know your recent paper that was PRACT and RVT that is a behavior colonial policy that use end-to-end training, and it shows promising results in both simulation and real-world environments. But it's limited, especially in real environments, because it needs a lot of data to scale up. And recently, some people from Stanford that like was posted that they can compose a lot of powerful models like 2D foundation models as a large language model. They can even use a very few training in the loop, and they can achieve very promising results, or with zero-shot generalization ability. And so my question is, how do you view that end-to-end training or just composing these large models? Which one is which one is better? Yeah.
I don't know. I think both are totally valid approaches, right? So if you go to things like RVT, perceiver actor, the advantage is that they're really good at replicating those demonstrations, similar to also these diffusion style models, with the caveat that it's kind of keyframe based, so less of the continuous interaction. And you could imagine scaling those by training them not on 10 examples, but what happens if you train them on 1 million examples? Then I think those representations have the capacity to also actually generalize very well. We just haven't done that yet, because so far the work has been either sim to sim or real to real kind of. So scaling, and they have underlying, as you know, transformer models. So I don't see a big problem with scaling with these. At the same time, I think these other directions are also super promising, right? Like where you're using LLMs either for starting to do kind of reasoning in the spatial domain, but also even, as I mentioned, there's this like Eureka kind of work where you're using LLMs to generate code for reinforcement learning, reward generation, and things like that. So I think we just gotta explore them all. It's right now, it's so hard to predict what's gonna be the ultimate solution, and there are so many super exciting tools out there that we can use, and it's not clear what's gonna be the final winner, if there's gonna be a final winner.
Any other points? Okay.
Thank you. I got a question, especially for Scott and Ross. So Ross told us that you don't see the reason why learning-based methods couldn't go all the way down to the control. And Scott told me that like all the components Boston Dynamics use can be replaced by learning-based. You just use human in-the-loop learning. So I would say that maybe times at 2023 is much different when you guys started Boston Dynamics. So if you were to start Boston Dynamics now doing for Atlas from scratch, would you change your tech pipeline, like for all the computing advantage brought by NVIDIA and simulation parts? And for us, I'm surprised that you are telling us that you don't see the reason why learning-based methods couldn't go all the way down. So I wonder what changed your perspective on that, or maybe you haven't changed. I'm not sure. Yeah, thank you. Yeah.
So I guess a large part of what we're doing right now anyway is focused on using machine learning to generate robot behavior. So yeah, I guess if we were to completely start a new quadrupedal robot product from scratch, from nothing, I think we've probably seen enough evidence specifically in the literature around the platforms like that RL is maybe a plausible approach to go from the get-go. For humanoid robots, I think it would be a pretty bad idea right now. It's not to say that eventually things will get there. I don't see any reason why not, but you can still make a ton of progress by having model-based control as the sort of the thing that's above the bare metal, and then using learned components in order to interact with that system in order to create interesting behaviors. And so, yeah, I mean, one of the things that we're doing is trying to maintain a high degree of flexibility in how we apply learning and model-based control together in order to do things with our robots. And so, you mentioned things like highly scalable simulations, rethinking compute platforms on robots to better line up with the types of models that we use for perception and now nowadays control. These are all things that we're doing, and we're moving forward and not just sticking to how things happened to be 10 years ago.
Okay, so let's see. I think I've always been open-minded, and I'm still working on model-based control. So maybe if I could express my philosophy, maybe, let's see. I think some of us have been doing control for a really long time. I think I believe that there's a few truths to the control problem, and we should be searching for those truths. And there are many different lenses by which you can try to study those truths, okay? And in some cases, today, right now, I have better tools where I start from models and I understand their structure, and I can zoom down, understand the optimization landscape, and I can see deeper things through the lens of model-based control. And there's other things like this common sense robustness that I can't see with those tools, but I can see a bit of. It's kind of foggy, right? But when I'm seeing results that are coming out that are changing my worldview in ways that are helping me understand those truths, I will always follow whatever path helps me try to understand the core problems. And yeah, so I think things have changed, and I've always, I did learning for my thesis. It's not like I just started doing learning, but I will continue to pursue as aggressively as I can the things that I believe will teach me the most about those sort of fundamental truths.
Hi, Russ. This is Jinda from Honda Research. I have a question to you. So as you said, behavior cloning policies are really powerful right now, and you can copy an average human skill in maybe 60 episodes, right? But my question is, are the two skill levels the same, like the learned policy and the average human skill? I think in terms of generalization, BC policy are still very much lacking, right? So what do you see, how to bridge this skill level gap in terms of generalization? Thank you.
Okay, yeah, thank you for the question. So when we talk about training one skill with 60, which 60, by the way, is crazy small number of demonstrations, right? But 60 to 100 demonstrations, then we are nowhere near the generalization capabilities or robustness that a human does. The fact that we can play these things out reliably, move bowls around and stuff like this and accomplish the task is already shocking to me, but it's nowhere near the robustness of a human. Okay, now when you start training multiple skills and you do the multitask thing, then we're not there yet. We're working hard on it. RTX, these kind of models, we're all kind of working towards this big multitask version. And that is the place where I would guess, even if, that I'm optimistic that we're going to get a different type of robustness out. Will it compete with humans? Eventually, I would be surprised if it doesn't, right? Yeah.
Thank you.
Mike?
Hi, I'm Jim from Apple. So I have a question about how to go beyond data. So basically, let's say in some safety critical scenarios or cases, we already know that maybe an average human cannot achieve the performance we want to get, right? How do you think we can combine the model-based approach with ML to go beyond human performance?
Well, so not only the average human may not be safe, but even if the average human is safe, your learned policy from human data may not know what the average human will do. So, right, it's even bigger safety problem when you're actually running a policy. And that's a really good example why you should do something model-based, because if it's not in the data, it could only come from the model because there's nothing else. And the way you do it is probably some ensemble thing, because the old robust control ideas of, you guarantee that nothing bad is ever going to happen, that basically works for linear systems. And we couldn't really push it that much further. But with ensemble methods and a lot of sampling, you may be able to do it in simulation.
I think if we're talking about behavior cloning specifically, that's the place where you feel like, there's a ceiling, which is human level performance. But actually, one of the first results in behavior cloning is that you can surpass human performance. with behavior cloning, right? So for various reasons, possibly by interpolating between multiple experts, but even in a single expert case. So I don't know that the ceiling is obvious, but I also think behavior cloning isn't, I wouldn't bet against behavior cloning going a very long way. We'll maybe talk about it in the debate later. But I think we can do better too, right? We can improve, we can label failures, ask humans to fix the things that went wrong on the first time. So maybe the original human demonstration had limits, but we can do better. We can certainly bring in more of our, advanced tools. We can optimize, we can use RL on the fly, but I can build models and I can work on those. So I think we will be able to surpass humans, even with the pipelines that we're talking about here. But I also would say matching bad human performance is just going to be so valuable that we must do that first. Right?
I mean, maybe coming to the question about, or rephrasing the question a bit, like how do we know when our models don't know, right? That's maybe the core. And I think that's probably a problem we are generally not very good at, not just for robotics, but all across the board, that they fail and they often don't know that they fail. So I think maybe this is what you were alluding to, sort of having some uncertainty estimate in the output of the model could help there, but it's, I don't think this has sort of really taken off yet as a technique, not in general, not just for models for control.
There's at least one good paper this week called No. It's exactly about that. Yeah.
Maybe you want to repeat this on the mic.
I know Alan, who is back there at some point, but Alan Wren has a paper about No this week. That's KNOWNO. Yeah, know what you don't know.
I withdraw what I just said.
No, it's first paper, yeah.
And I think in general, it's going to be harder and harder to really evaluate those systems, right? The more complex the tasks are becoming too, and more open-ended the tasks are. If you think about the issues with autonomous driving, right? Like how do we evaluate whether they work or whether they don't work? How does a city decide whether they let the cars drive autonomously or not, right? It's just extremely difficult because you can't just come up with a kind of set of tests and then say you have to pass that, right? And these kind of, you have to sample scenarios and you have to kind of experience it over time. And also at some point, there will just maybe some kind of trust, right? Where you say, okay, we'll hope you've done enough testing and things like that. It's just getting harder and harder. And the same will be if we want to put mobile manipulators somewhere, right? It's also going to be really difficult to prove that they are safe and that they would never do anything wrong.
But actually, maybe we don't have to prove. So actually, driving is a great example. You don't have to prove you're perfect. You have to prove that you're better than humans. I have a lot of statistics on how good humans are, how often they get into an accident by like millions of miles driven or whatever. So as long as you show that you're better than humans, why not? Same thing, like let's say you put 1,000 robot arms in an Amazon warehouse versus compared to a number of workers that cost the same. How many packages get shipped? That's what you care about, right? So comparing to humans is probably good enough. You don't need absolute guarantees because humans are not absolutely guaranteed either.
Now, the tricky thing is in the driving, for example, it's just even figuring that out is extremely difficult because you have to put them in these situations, which you want to first check out whether they're safe enough to be put into those situations in the first place, right? And what are the use cases? How do you really develop those benchmarks and tests and all of that? Is just, I think, an extremely hard question. And of course, they just have to be as good as humans is also, from a rational perspective, that's true, but from a perception, how the public perceives this is of course not true, right? Even if these cars might be as safe, if they show certain failure modes where you might say, well, a human would never have done that, that's already really bad, even if on average they're better or something like that.
I think we're kind of over time. We can take one last quick question.
Hi, John from DeepMind. I want to go back to that data question. So earlier, I forget if it was Scott or Russ, was talking about how we will probably need to do some sort of policy improvement at scale And the conversations I've been having, certainly, I think people are anticipating the end of the BC era. There were rumblings about that. What are the tools? What kind of discussions are going to be having in 2 years about this? If we come back to Coral, what skill sets should people around here be optimizing for that kind of research they're going to want to do then? And it will draw on the model-based toolkit, perhaps, to some extent?
It's already the end of the BC era? Wow, that was fast. Let's see. So I think being well-versed in the toolkit that's apparent right now is absolutely a requirement for anyone who's studying in this area, right? So I think you don't want to over-specialize to one narrow corner of RL or one narrow corner of BC or know nothing about model-based control. Maybe in the long term, one or a couple of these techniques will win out and you won't have to worry about the other ones. But I think in the near term, if you're going to be making progress and creating new robot technology, you're going to be using a mix of these things. And I think they each have their place. I think, behavior cloning might be really good for programming, in the short term, very specialized skills that are well outside of our representational capabilities of model-based control. Doing sort of whole body dynamic coordination, lifting heavy stuff. As you can see, we can get pretty far with model-based control. And if your only data source is something that isn't an embodied robot, it's maybe human demonstration data, then that could be a place where RL really adds a lot of value. If you have good simulation and good demonstrations in order to guide exploration of an RL algorithm, you can actually produce pretty high quality behaviors that don't look weird and things you might actually want to run on a robot.
Just briefly, I would hope that we're getting to the level where behavior cloning gets you to perform very well in the real world, but then there'll be fine-tuning in the real world, right? How to do that very, very effectively and very well with the lack of supervision that you might have. And I think at some point, hopefully, that these robot systems are going to be capable enough at the tasks they were trained on through behavior cloning that they have transferable models, internal models, so that we can really start looking into learning new tasks, right? Lifelong learning, looking at new tasks and leveraging the things that the system already knows how to do exploration in this task and come up with new policies and things like that. I think that'll come afterwards. So maybe that's why a lot of the RL and things like that had trouble working in many of the real world applications, is just because they were often starting from scratch, right? But if we're starting from that level that we can reach through behavior cloning, I think then maybe we can revisit all these areas and make real progress.
Just a very general answer to that question. Your job as a researcher is to come up with unique things that the whole herd of researchers hasn't thought of. So when you come back in 2 years, surprise us with something that's completely different from what we're talking about here. There is no need to recycle the existing toolbox in one more permutation and build one more system. We've got a bit of that, a bit of that, a bit of that, and put it together. And here, there's the next video. Ideally, we want new things. So find what the crowd is doing, do something else.
I had a comment, but I think after this beautiful closing statement, I think
with that, let's give the panelists a big round of applause.